Hey, hello and welcome back everyone. Moving on to section 3.3, a little bit of a quicker section, which is probably a good thing the way we've had sections lately. Talking about separable, in reality separable ordinary differential equations. The title of the section, I'm still giving it the name continuous dynamics because these are a subset of continuous dynamics. But really we are analyzing what I have in the first definition here, which is the separable ordinary differential equation. And I'll use the acronym ODEs for ordinary differential equations. The way these look, they look very similar to our initial value problems for integrals, right? Looks similar to the IVPs for integrals, but there's a very subtle difference here, and that subtle difference is happening on the right-hand side of the derivative term. Well, the derivative's on the left, but in terms of the IVPs for integrals, there was just a function of time on the right-hand side, and what we've done now is we've multiplied that function of time by a function of y of t, and y of t, of course, being what we want to solve for. Or in other words, this is the quantity we want to predict. So now there's a function of that quantity which is occurring on the right-hand side. It's been multiplied by the function we had before. So we made our lives a little bit more complicated, and we're going to see that the solutions are a little bit more complicated, but it's important that we have the ability to solve equations of this form. Reason being, which I describe in the next section, where in the case of IVPs for integrals, we almost are asking too much out of the equation itself. We're asking that we can predict the evolution of the quantity for all amounts of time, right? We can predict what the change in the quantity is at all points in time, and that's not always the easiest thing to come up with. Finding this function in and of itself. On the right-hand side, assuming that g was equal to 1 in this case, having perfect information of what the derivative of our quantity we care about looks like is really strong information. And so the separable ordinary differential equation says we don't need perfect information. What we're actually looking for is how a measured quantity evolves over time, which is going to be its derivative, right? We're asking, can I relate that change to itself, right? If I can relate the change of a function to itself, change in function is somehow related to itself. G captures that relationship. This relationship is saying G, right? G could be squaring that quantity, it could be dividing the quantity by 10, it could be subtracting 8 from it or something. Whatever G does to its input is the relationship of the quantity to its derivative. And then there's what is F doing in this case? F ends up playing the game of the magnitude of the relationship, right? So F is sitting outside. It's saying, well, if F is large F means that y prime depends strongly on itself. Of course, according to G still. And then a small f would be weakly in magnitude, right? So if f were close to 0, it would say that the change is very weakly related to itself. But if f gets to like 27 or something, or 2 million, then it would be strongly related to itself. And that magnitude, you'll notice, is a function of time, so we're allowing the magnitude to vary over time. Today, my quantity, which maybe I'm measuring the eggs that my chickens produce, maybe that quantity is weakly related. The change that they've done is weakly related to how many eggs they have currently in the coop. But maybe tomorrow it's strongly related to how many eggs they currently have in the coop. So it just depends on what you are able to measure in kind of this overall relationship between the change in a quantity and itself, as well as the magnitude of that relationship over time. But that's a weaker assumption than knowing perfect information. If I just write it like this, F here is just perfect information on the change of the quantity, which is a really strong assumption to make. We normally don't have that strong of an assumption. So this is very slightly weaker. We still need to know how the quantity is related to itself through G, as well as the magnitude of that relationship. But we'll see situations today that describe cases when we can relate a quantity to itself, as well as the magnitude, which evolves over time. So let's look at the solution. I mentioned before that this is a little bit trickier than integrating all by itself. And in fact, it's quite trickier. So what you see on the screen right now is the solution. And we do have integrals, right? At the end of the day, all differential equations, meaning if you start with an equation that has a derivative in it, will be solved with integrals. You can guarantee yourself that there will be integrals. You have to get rid of the derivative somehow. You're going to do that with integrals, but they can get complicated on how they have to be applied. So in this case, I'm going to go through what's on the page right now. We're going to scroll down later. We're going to see there's actually an easier way than what is introduced right now. This is maybe a little bit intimidating what you see right now. You see some inverse functions as well as just a whole bunch of terms. But I'm going to go through this, and then we're going to see maybe what the slightly easier way of thinking about this is. So if you like this, then let's go for it. Our solution y is going to depend on, well, here's my initial value, just like I had before with initial value problems. That initial value ends up inside of a function that we call capital H. Now, what is this function capital H? Capital H happens to be the antiderivative of the reciprocal of g, right? And g was that g in the original differential equation we have. So you have to compute the antiderivative of the reciprocal of g. That's where the initial value goes. And then I also have this term capital F, which is where the initial time goes. So the initial time goes into capital F. Capital F is not too surprising how we notate it. Capital F is just the antiderivative of lowercase f, meaning this one right here. And our initial time goes into capital F, as well as our future time, right? Because t is kind of interpreted as our future time that we like to predict something at. That also goes into capital F. And then we are forced into H inverse as well. So there will be an inverse function, the inverse function of capital H, where, still capital H is defined as this antiderivative. But of course, over here, I've reminded the reader of the definition of an inverse. And please recall, I've got a video on it. We went over it this semester. Inverses of functions are not reciprocals. So do not consider H inverse as 1 divided by H. They're not the same thing. H inverse of x is not the same as 1 divided by H of x. Do not get those mixed up. They're not the same. Okay, so that's where all those terms come from. And if you want to go ahead for every single one of these separable problems and solve our 3 terms here at the bottom, if you label that 1, 2, and 3, recall that computing inverse functions is not necessarily an easy thing to do. But if you want to go through those 3 steps of calculating all 3 of those objects and then just plugging them all into your formula, including your initial value and your initial time, you will get the answer right. So if you're excited to do exactly what I've got here in the proposition, I would do exactly that. If you don't feel like doing that, there is an easier way, or at least slightly more common way that's taught to solve these separable ODEs. I do have a proposition claiming and showing that they are indeed dynamics. So going back to the first section of this chapter, we have our very nice ability for dynamics to kind of merge time windows together, and these solutions would do that as well. I'm not going to go through that here either. You can look at the proof if you'd like to. The step-by-step solution approach is the one that I think a lot of students like a little bit better, and they think it's a little easier than just computing each of the pieces, capital H as well as its inverse, as well as capital F, and just plugging everything in. The step-by-step solution approach really does give you a grasp for how the solution is the right answer. So we're going to look at that. We're going to try to solve that ODE that's sitting at the top, and the steps that we're going to do to solve that ODE are as follows. So step 1, we're going to rewrite the derivative as dy over dt, okay? And we're going to rewrite every y of t just as a variable y, okay? So in some sense, we are omitting dependence on t, even though it's there. That dependence is still going to be there. It's still always a function of t. We aren't predicting the future, but we're going to remove it for now. It's going to make our life easier if we remove it. And so what happens if I look at this equation and I replace y prime with dy dt, and I replace this y of t just with y? Well, we end up with the equation dy dt equals f of t times g of y. And the reason why I do this, and in fact the entire reason why these are called separable ODEs, is that we have officially separated our variables. There's really 2 variables hiding behind here, right? The variable y, which is dependent on the variable t. We've separated those 2 variables into individual terms by doing this. So we've got the dy variable as well as the g of y function. And we have the dt variable and the f of t function. And there are kind of 2 cases of separations here. There's one which is a division on the left, right? They're separated by a division on left, and they are separated by a multiplication on the right. Okay, so that's really what we mean when we say separable ODEs, is that we have the ability to separate the variables of the ODE. And once we do that, in step 2, we ask ourselves to rearrange the equation so that all terms with y's are on the left-hand side and all terms with t's are on the right-hand side. Okay, this is really re-emphasizing that separation of variables. At this point, what do I have to do? I have to divide by g of y, so that's why I end up with a 1 over g of y. I also have to multiply both sides by dt, and that's why I end up with a dt on the right. And in this case, I've truly separated my variables to, well, all y's are on the left and all t's are on the right. So once again, this is why we call them separable. And now that our variables have been separated, we can integrate both sides. And so we're going to plug an integral sign on both sides, and it looks like an integral of 1 over g of y dy. This is really why that capital H of y was showing up earlier as the antiderivative of the reciprocal of g. And then we also have the integral of f of t on the right-hand side. That's why our capital F was showing up earlier. So that's why those two functions were showing up earlier, the integral of the reciprocal of g as well as the integral of f. And then in step 3, we are going to integrate both sides of the equation and just compute those to be whatever they are. And at this point, things start getting a little bit abstract still, but when we get through some examples, it'll be clearer. I am going to name, this integral of the reciprocal of g. I'm still going to give it the name capital H of y. So we'll just give that antiderivative the name capital H, and then the antiderivative of lowercase f, we're going to call capital F, of course. And you could ask me, why don't we have a plus c on both sides? Well, we would have a plus c1 on the left and plus c2 on the right, because there would be 2 total copies of plus c because we performed 2 integrations. But then I could go ahead and just subtract c1 from both sides, and they would cancel on the left, and I'd be left with c2 minus c1 on the right. But they're both arbitrary constants, so it's like, even if c2 were 7 and c1 were 3, c2 minus c1 would be 4, which is still just a new constant. And so I'm combining all those constants into this plus c on the right-hand side, just saying like it'll get figured out eventually. We don't have to worry about its value yet. Okay, but at this stage, we've basically solved the particular ODE, meaning this one, y prime was equal to what? F of t times g of y. It's an implicit function. If you remember your implicit derivatives section of Calc 1, this is an implicit function of y and t. So that solves that particular ODE, but let's keep in mind these are initial value problems. And so we have the initial value, which is always included, y at t0 is equal to x. And so our integration constant, our c, our value of c, will be chosen so as to satisfy this initial condition that y at t0 is equal to x. Okay, so what do we have to do to make sure you can choose c to make that equation true? Well, what we have to do is we see that equation says y is equal to x, so we're going to plug an x in for y, and in fact the equation also tells us that t is equal to t0, and so we're going to plug a t0 in for t, and then we're going to solve for c. And in fact, if you can already see it in here, if you solve for c, what do you get? You get that c is equal to h of x minus f of t0. And if I scroll all the way back up to our solution formula, that I don't really think we need to use, here we have c is equal to h of x minus f of t0. That's the c we just solved for, the plus c we solved for. But you'll see if you ever do this concretely, if you do it with an actual example, that's not really the form they take. The c is just going to end up being a number, like 8 or -5 or something. Okay, but in that case, you can solve for c, which we're doing in step 5, and I did just do that. And we're going to use that value of c in the solution that we've technically already had. And so if I plug that value for c in my solution, what do I get? Well, I get h of y is equal to f of t, and then the value for c I just computed, which was minus f of t0 plus capital H of x. And now you can almost see it at this point. If I just computed an h inverse on both sides, what would I have? I would have y is equal to h inverse of a capital F of t minus f of t0 plus h of x, right? And that's the solution formula I gave you all right away. And that's what I say at the bottom here too. So you use that value of c and you get exactly this h of y, and then you finish by solving for y. But solving for y is computing the inverse. If you go back to that section in this collection of videos where I do describe computing inverse functions, I also talk about how computing inverse functions and solving equations is actually the exact same mathematical procedure. So in reality, when we're doing this in the step-by-step process, you should think about this step as solving for y. You should not think about this step as computing an inverse function. And we're going to see that when we get through our examples. So that's how you get to the solution formula using a step-by-step process. And we're just going to go through that step-by-step process now in all of our examples. And it's going to make a lot of sense when we actually do the examples, I promise. So here's our first example. We're just going to look at the separable ODE. Y prime is equal to t squared times y, and its initial value is 1 at the initial time 0. Now, if I follow my step-by-step process, my first step is asking me to rewrite y prime as dy over dx, and it's asking me to rewrite y of t just as a y. And so we're looking at the equation now, dy dt is t squared times y. And then at step 2, we want to rearrange it so that all terms with y's are on the left-hand side, and all terms with t's are on the right-hand side. And let's recall where we were. We had something like dy over dt is a t squared y. And what would I want to do? I'd want to divide both sides by y. That's why I end up with a 1 over y on the left. And I'd want to multiply both sides by dt. That's why I have a t squared dt on the right. In step 3, we want to integrate both sides of the equation. So we're integrating 1 over y, and we're integrating t squared. And if we remember our integrals, 1 over y is going to be the natural log of the absolute value. T squared is going to give me t cubed over 3. And as I said before, you could always have 2 constants, but they're going to reduce to only 1 constant anyway if you end up solving for y. So just put 1 constant on the t side, and we end up with our implicit solution, log of y equals t cubed over 3 plus c. And at this stage, the only thing that's undetermined is the value for c, so we're going to recall this. We're going to recall our initial value to try to solve for c, and the initial value says, oh, by the way, when t is equal to 0, y is equal to 1, okay? So when t is equal to 0, y is equal to 1, which means in this formula, my initial value says when t is equal to 0, y is equal to 1, and that should help me determine what c needs to be equal to. So I plug in 0 for t and 1 in for y. The log of 1 is 0, and you find out 0 equals 0 cubed over 3 plus c, also known as c is equal to 0. So now that we know c is equal to 0, we go ahead and plug it in to our implicit solution. We plug in a 0 for c, and that's going to put a 0 in for c. It's going to tell us log of y is equal to t cubed over 3. And we can finish off by, in step 7, solving the equation for y, right? And this is where I was saying you have an inverse function here, but you shouldn't think about it as the inverse function. You're just looking at, once you've determined your value for c, just solve this for y. How do I get rid of a natural log? I take the exponential of both sides. Those are going to cancel on the left. You find out that y is equal to e to the t cubed over 3. So y is equal to e to the t cubed over 3. Let's just verify really quick that that does actually solve the initial value problem we were given. I'm claiming that this is the solution, e to the t cubed over 3. Well, let's check the first equation. Let's check if this is true. What happens when I take a derivative of e to the t cubed over 3? Well, the derivative of the exponential is itself, right? I'm going to use the chain rule, but the derivative of the exponential is itself, so that's going to give me e to the t cubed over 3. And then the chain rule says multiply by the derivative of the inside. I'm going to multiply by the derivative of t cubed over 3. That's going to give me 3t squared over 3. Those 3's are going to cancel, and I'm just going to be left with, e to the t cubed over 3 times t squared. But what is e to the t cubed over 3? Well, we already know that that's y. So in fact, this is equal to t squared times y of t. So yes, this is exactly true in the first case. Is the second initial value portion true? Let's evaluate at 0. That's going to be e to the 0 cubed over 3, also known as e to the 0, also known as 1. And so yes, the second initial value is also true here. So we've done a good job solving our separable ODE. Let's look at a second example, quite a tricky one. I've included this example more or less to say, we're not teaching you a bunch of integration techniques for no reason. These do show up. I mean, all of these dynamics, we're trying to predict the future. All of our integration techniques do need to be used if we're going to do a good job predicting the future. So I've presented a fairly tricky one here, but we'll see if we can do it. So let's go ahead and follow our step-by-step process again, which basically starts out with us saying we're going to replace y prime with dy dt, and we're going to replace every case of y of t just with y by itself. I don't want it to be y of t anymore. So what I end up with is dy dt is equal to t times root t minus 1 over y times e to the y squared over 2. In step 2, I'm going to want to solve that expression so that I can move all terms of y on the left-hand side and all terms with t to the right-hand side. That's going to give me, on the left-hand side, if I multiply both sides by y, e to the y squared over 2, I get y e to the y squared over 2 dy. And if I bring the dt to the right-hand side, I'll have t times root t minus 1 dt. In the third step, I'm going to integrate both sides of that equation. That's going to give me the antiderivative of y times e to the y squared over 2 is equal to the antiderivative of t times root t minus 1 dt. I'm going to have to solve each of those antiderivatives individually because they're not that easy. How could I solve the first one? Well, if I think about it, for u substitution, if I took a derivative of y squared over 2, right, d dy of y squared over 2 is going to give me y. And there's a y sitting right there. So I'm probably going to want to use u substitution here, with in particular the value u being y squared over 2. So that's going to give me an e to the u, and then du is just going to naturally be y dy, what's remaining there, so I'll just have a du. The antiderivative of e to the u is still e to the u. And so this antiderivative on the left-hand side is e to the y squared over 2 plus c. If I want to take an antiderivative of t times root t minus 1, yeah, I can do that in a couple ways. I can either do u substitution or I can integrate by parts. Integration by parts seems a little more straightforward. It's a multiplication of two terms, and I certainly know how to take a derivative of t, and I also know how to take an integral of root t minus 1. And so I'm going to use integration by parts on this. The derivative of t is just 1, so there's going to be a 1 there when I take a derivative of that. The antiderivative of root t minus 1 is really a u substitution where u is t minus 1. Antiderivative of something to the 1/2 power will be that thing to the 3/2 power divided by 3/2, also known as 2/3 t minus 1 to the 3/2. And so that's where my 2/3 t minus 1 to the 3/2 cases are coming from. Then I'm going to have one remaining antiderivative from my integration by parts. I'll have to integrate t minus 1 to the 3/2 one more time. So I'm going to add 1/2 to that power of 3/2. Gives me 5/2. I'm going to have to divide by that new power. Dividing by 5/2 is the same as multiplying by 2/5. And if I then simplify everything, and it's not the prettiest, but if I simplify everything, I end up with 2/15 times t minus 1 to the 3/2 times 3t plus 2. You could, of course, leave it as unsimplified as you wanted and just leave it up there if you would like to. It's going to make it a little bit easier to find the constant c if you simplify a little bit. Okay, so all that said, what have we actually done? We computed the left-hand side's antiderivative as e to the y squared over 2. We computed the right-hand side's antiderivative as 2/15 t minus 1 and 3/2 times 3t plus 2 plus c. We're going to actually substitute both of those in, and we end up with our implicit solution, right? This is the implicit solution to the ODE, but it doesn't meet the initial values yet. Right, as long as we have this plus c sitting around, it means we haven't hit our initial values. And so to hit our initial values, we have to go back to the original and find out what our initial value was. It looks like at time 2, we're supposed to take the value 0. And so I'm going to plug in time equals 2 into my implicit formula. That's right here and right here. I'm going to plug 2's in. And what was the value of y? Well, the value of y had to be 0 at that time. So I'm going to plug 0 in over here, 2's in on the right. And how does everything simplify? Well, you find out that e to the 0, which is 1, is equal to 16/15 plus c. Well, at this point, if I have the equation 1 equals 16/15 plus c, I can just subtract 16/15 from both sides. You find out that c has to be negative 1/15. Well, since c is negative 1/15, we can go ahead and plug it in up here, negative 1/15. And now we have an implicit solution which includes the initial condition. And then we just need to solve for y. Our last step in step 7 is going to be to solve for y. If I scroll down to the next page, we're going to finish by solving for y. When we solve for y, we're going to take the log of both sides because we initially had exponentials in front of y. So we're going to take the log. That's going to cancel with the exponential. I get y squared over 2 on the left and a log of everything I had on the right. Now I'm going to have to multiply both sides by 2. And then finally, I'll have to finish by taking a square root. So I take a square root, but I do have to be a little bit careful because I'm taking the square root only a plus or minus sitting around. And so now we do have to get into that little bit of weeds where every time we have an inverse function, or really a square root, something that's multi-valued, anytime we perform an operation that has 2 answers, we have to somehow figure out which sign to take or which specific value to choose. So here, the way that we're going to figure out which value to choose is that maybe the ODE was modeling a real world measurement which only takes positive values, right? We're trying to predict the future here. And maybe, this value y that we were trying to solve the ODE for the whole time, maybe it's trying to predict the distance between a car and a house, for example. In which case, well, distances can only ever be positive. And so kind of that intuition, the physical intuition is telling us, oh, you have to choose the positive number. But on the other hand, maybe there's a case where it's a physical intuition where y was maybe talking about electric charge or something, and especially the electric charge of an electron is going to have a negative sign on it, in which case you want to put the negative. But this is where the physics actually starts to play a role, or the real world situation starts to play a role. We can't only be mathematicians in the real world, right? Because we will end up with some problems, some specific models, which produces 2 solutions. Okay, and you have to be that very slightly real world mathematician to say, okay, the math says there are 2 solutions, but the real world's only going to predict one future. There's one future that we're all going to exist in. Which of the 2 solutions is more likely? Well, it's the one that agrees with physics. And so you end up presenting that as the possible future of the 2 of them. And so I just have this mention that both are valid answers, both could be the answer. It's up to us to decide in some physical situation if somebody actually asked us to do this. So finally, we're going to present one real life example of, computing separable solutions to ODEs. And this is a pretty nice one, going back to the biology department. We've kind of been interacting with all of our departments lately. So this one's going to be some soil saturation in the greenhouse. And so our biology department is a little curious about the saturation levels in the soil in their greenhouse. At 6 a.m., a research assistant is required to fully saturate all of the soil in each plant pot. So what do we know? We know that the initial value of the saturation, right, if y describes saturation, then at 6 a.m., so 6 is my input, I have a saturation level of 100%. Over the span of the next 2 hours, they've gone ahead and measured the rate of change in soil saturation, and it looks like the rate of change is going to fall. Well, that makes sense because plants are going to take up the water, so they're going to be negative, and they're going to be negative proportional to the current saturation level, so that means they'll be proportional to YT, as well as the time since the pots are fully saturated, so T minus 6. And we're going to go ahead and use that to construct our initial value problem, or a separable ODE. So it says that the rate Y prime of T is proportional to the current saturation level Y, as well as the amount of time it's been since they've been filled, T minus 6. And so that is going to be our ODE here, T greater than 6, but we do need an initial value here, but we've already been given that initial value. It says that Y of 6 is equal to 1. So specifically at T being 6 a.m., we know we are 100% saturated. And so what we have here is a separable ODE that we can solve and tell the biology department how well saturated their plants are as time moves forward. And in fact, the biology department has asked us to construct a plot of the saturation levels so that they may interpret it and decide when to water the plants again. So we go back to our separable ODE, here it is. And in particular, we can solve it using the step-by-step process. So the step-by-step process reminds us to replace y prime with dy dt, as well as y of t with just y. So when we do that, we end up with the equation dy dt equals 6 minus t times y. And we're going to rearrange this so that every term with a y is on the left-hand side. That means I'm going to divide both sides by y, give me 1 over y. And we're going to have every term with a t on the right-hand side, so I'm going to multiply both sides by dt. And then I'm going to integrate both sides, which is going to give me 1 over y is equal, integral of 1 over y is equal to the integral of 6 minus t. And when I actually perform that integration, we find out that the natural log of y is equal to 6t minus t squared over 2 plus a constant. If I'm going to be able to meet that initial condition, let's recall what it is. It's that y of 6 is equal to 1. Then I'm going to have to plug those numbers in and choose a value for c. So in fact, I'm going to plug 1 in for y. I'm going to plug 6 in for t. And we find out that the log of 1 is equal to 36 minus 18 plus c. 36 minus 18 happens to be 18. Log of 1 is 0. We find out that 0 is 18 plus c. Or in other words, c is negative 18. And we can plug that value in for c. So now this equation simply needs to be solved for y, and we will be finished. If I solve that equation for y, I'm going to have to take the exponential of both sides. That's going to give me that y is equal to e to the 6t minus t squared over 2 minus 18. We can plot it from this point, but I went ahead and simplified just a little bit. It turns out you can simplify 6t minus t squared over 2 minus 18 as negative t minus 6 squared over 2. That makes it look just a little bit prettier. It makes it very clear that when you plug 6 in for t, you get e to the 0 power, you get fully saturated. And then it decays, right? It decays as the exponential of a negative quadratic. And so we now present the biology with the following chart, which shows that our saturation level starts at 100% at 6 a.m., just like we expected, and it falls dramatically, getting really, really close to 0% by 10 a.m. And so what they've discovered here is that maybe some plants that need to be watered more often, or shouldn't ever have dry soil, need to be rewatered at 10 a.m., about a 4-hour period. So that's what we've been able to consult the biology department as. Hope it was fun. I really like this section. You can see how applicable all these are. Next section, we're going to move on to asymptotics. We're going to split it up into 2 videos, actually. But we've got equilibria and blow up. These are 2 very important topics to talk about when it comes to predicting the future. Anyway, I'll see you then. Have a good one. Bye.